Okay guys, let's talk about the results here. And so I put up on the board the 3 scenarios that we had. And so let's talk about the water one first. This is the one where you should have had the least change in mass compared to the other two. Nobody had, as I walked around and looked at people's results, nobody had a 0% change in mass. When you guys made your hypothesis, is that we have hypothesized that this was a what kind of solution? What did you hypothesize? Isotonic, yeah, and so it is an isotonic solution because you have distilled water on the inside and distilled water on the outside. So, but in walking around, not anybody had 0% change in mass there. And in all my years of teaching and performing labs like this, I've had one group ever get 0% change, all right? So it doesn't happen very often. So let's talk about why that is. Why might you, I noticed that some groups gained some mass, some groups throughout the day lost a little bit. What is, what would be the reason that we have this kind of variance there? Mary, you have an idea?
There could be a change in the mass when you pull out the water,
Yeah, absolutely. So you might have some water still attached to it, especially at the ends, you know, inside the dialysis tubing there that could attribute to more mass. Anything else that could account for maybe not getting what we expected? Cole?
Air bubbles, that might have been a solution.
Okay, air bubbles. Yeah. Jay?
Maybe you didn't tie the ends of it tight enough so water would flow in and out.
Okay. Yeah, if the ends weren't tied tight enough, you could have some water leaving or entering there. Yeah, this lab has a lot of room for error in terms of that, and human error and so on. It wasn't tight, if it wasn't tight or not. So lots of things could have kind of went wrong there. And so, but doesn't change the fact that it should be isotonic. And so like I said, it doesn't happen very often that we do get 0%. I think this year, I looked at all the groups, the closest one had just a 0.23% increase, so it was almost, you know, 0.23% is pretty close. I had another group that was 0.94, I think, so some groups got pretty close in terms of it being isotonic. And also, realistically, theoretically, the rate should be equal going into and out, so you should have a 0% chance theoretically. Realistically, also at any given time, there may be a little bit more on one than the other, and so it might not be exactly equal, and so to get a 0% chance is slim. But like I said, some of those like 0.23 and 0.94, and so it's pretty good. All right, so regardless, this should have had the least change out of all of them, all right? So then as we move on to the sodium chloride and the sucrose. So I mixed these solutions up. They were each a 1 molar solution. So there was a 1 molar solution of sodium chloride, a 1 molar solution of sucrose. Molar, 1 molar, that's molarity. A 1 molar solution means that you had 1 mole of the molecules in 1 liter of water. And so what is a mole? It's 6.02 times 10 to the 23rd molecules. And so there's a lot of those molecules in there. And so that's what molarity is, and that's why it's a concentration. So my question is that if you had a 1 molar solution of sodium chloride and a 1 molar solution of sucrose, the solute concentration is the same in either one of these. The solute concentration is the same. And so so if the solute concentration is the same, the solutes vary, sodium chloride to sucrose. What would we think about the water concentrations then? The solute concentrations are the same. It's 1 molar and 1 molar. How do we apply this? Remember when we went over the YouTube example? There's glucose and salt on one side and glucose and salt on the other side. This one had like a 2.1 molarity of glucose and sodium chloride combined. this had, I don't remember, 1.25 or something like that, glucose and sodium chloride solution. And so, how do we use this molarity to figure out water concentration? So if you have a solution on this side that has more solutes in it than the solution on this side, do you have a higher or lower water concentration on this side? Lower, right? And so my question to you is, if you have equal solute concentrations here in the solutions, the solutes are different. But there's still, so as a 1 molar concentration, then does it make sense that the solute or the water concentration should be close to being equal a little bit? All right. And so what happens is, my question to you is, why is it that you got the results that you should have gotten? And what are the results that you should have gotten? You should have gotten that this gained mass, it gained more mass than this, but this gained the most mass. So it kind of goes. So my question is then, they gained both of these, which means water went where? Into or out? Into. You have your higher concentration, it's pure water on the outside. Water went into. Why is it that the water over here, why this one gained the more than this one over here? Even though the molarity of the is the same. That's what you should have gotten.
Because NaCl has a bigger molecular mass.
NaCl?
Yeah.
Actually, it's just the opposite. Sucrose has a bigger molecular mass. Sucrose is C12, H22O11, and this is just NaCl. So this one actually has a bigger molecular mass. It's like 342 grams to like 50 something per, like grams per liter for molar concentration. Everybody has an idea? Let's go back to what's the question? Why, so everybody follow me that water went in both of these? All right. My question to you is, why did this one gain the most compared to this? So why did this, the percent difference? You should have gotten this as a higher percent difference than this. That's correct. All right. So remember that the dialysis tubing is selective based upon size, right? So the pores are a certain size here. And so the water is small enough to get through the pore, so water was going in here. Glucose is a much larger molecule than sodium chloride. So, sucrose is a much larger molecule than sodium chloride. So sucrose is too big of a molecule, it doesn't leave, and so water can only enter, all right, into there. Whereas NaCl, two ions, there it's forming an ionic bond, sodium chloride is small and therefore can fit through the pore, so sodium chloride can go out. Sodium chloride actually dissociates into the sodium ion and the chloride ion, and those diffuse out. And so you have the sodium chloride going out and water going in. So therefore, what's happening to the water concentration inside as this is going on? Is that water concentration going to go up or down as this diffusion is going on? Water concentration. Water's going in, sodium chloride's going out. What's going to happen to this water concentration? It's going to start going up, right? Can this situation possibly reach equilibrium? Yeah, absolutely. As sodium goes out, water goes in, that can get to a point where there's equal concentrations of sodium chloride inside and out. Same thing with water. Can this one ever reach equilibrium? No, because sucrose can't go out. And so therefore that the sucrose is staying put. So as water goes in, it's going to keep on going in here. Whereas this one, as the water goes in and the sodium chloride goes out, the water concentration is going up. So therefore less and less water, the concentrations are getting closer and closer to equal. And so therefore you have less gain. Does that make sense? All right. And so that's what we should have seen. All right, is your trend. So you guys' numbers varied and so on, but most groups as I went around had that kind of trend. All right, and so that's what we should have seen and why. Okay. So if you have like one of them that's kind of off or something like that, it's okay. Don't change your answer or anything like that. But so that's why we went over it. But in answering the questions, you can address what you got, but say that was wrong. It should have been this. All right. And so I want you to actually answer the questions as if you had right answers. All right. Or right results. All right. If yours was a little off there. So for the lab then, what is due on Monday is your questions for the lab. So the lab sheet, and notice, can I borrow yours, Kristen? On the back-hand side, it says answer all questions here or attach a sheet of paper. So your questions are at the bottom here, so you can choose to answer them here. If you'd rather have a piece of paper and attach it, you can do the same thing. Do that as well and just staple it. So that's due on Monday, as well as the first sheet that you picked up here today. So let's look at that for a second. It says Osmosis Challenge on it. That's the sheet I want you to look at. All right, so it gives you a little introduction, and I want to point out, so it says you are in the hospital and need intravenous fluids. You read the label on the IV bag, which lists all the solutes in the water. And then there are 3 bullets that have 3 questions. I want you to answer those questions. So these are application questions, so taking in what we've talked about in class and applying it to a situation with somebody getting an IV. And so I want you to remember we're talking about diffusion and osmosis, so in your answers it should be something about that, okay? All right, that these relate to. And then the rest of this describes an experiment and that I want you to analyze and kind of think about and apply what we've talked about in class to this experiment. And so so it's just some application questions, okay? So that in addition to the lab questions are due on Monday, okay? Any questions on that? Okay, so then what the rest of the hour we're going to do today is I'm going to teach you about something called water potential. Oh, there's a question.
For the lab, it says graphic results using.
Oh. Yeah, I meant to go over that. Every hour is asked that question. So let's just go over it. The graph is very, very simple. First of all, in graphing our data, the dependent variable goes on our y-axis. And the dependent variable is what you're measuring in the experiment. What is our ultimate thing that we came out with it number-wise that we got out of the experiment? Our measurements. What do you think? Yeah, your percent change in mass. So we're going to have our percent change in mass here. Your independent variables, what changes, and what we decided before and changed between our different groups. We had 3 different groups here. So really what changed is what was inside the cell, right? So here we have our contents of the dialysis tube. Now, let me ask you this. Does the percent change in mass that happened in this setup have anything to do with the percent change in this setup? No, these are independent. So does it make sense to do a line or a bar graph? A bar. All right, a line graph with points is you're assuming that there's a relationship between those points. And so we're going to do a bar graph. So we have 3 different contents. We have distilled water, NaCl, and sucrose, and you have your percent change in mass. Okay? All right? So that's it. Thank you for asking that. Any other questions? Okay, so so we are going to discuss this water potential thing. So we're going to add on to what we know about how water moves. So far, we've been focusing on solutes and figuring out solute concentration and there indirectly water concentration and looking at water diffusing from high to low concentration. We're going to see that there's something else that plays a role in that. So we're actually going to write some notes. So you're going to actually get out a piece of paper. All right. Water potential is not in our textbook, but the College Board says you need to know it. So I'm going to teach it to you. So water potential, you can think of it as the potential for water to move from one solution to another. So water, pure water, like in this sodium chloride example here, let's use sucrose example. Pure water has a higher water potential. There's no solutes. All the water molecules are free. They're bouncing around and they can hit the membrane and diffuse into the cell. Whenever you have solutes, some of those water molecules are going to be hydrogen bonding and attracted to the polar parts of that molecule, forming hydration shells and so on. So there's fewer molecules of water free to hit the membrane and go in this direction. And so therefore, whenever you have solutes, you have a lower potential for the water in that solution to move into the other solution. When there's no solutes, you have a greater potential for the water to move in the other solution. And that's kind of how I want you to think about water potential. So let's write a definition about water potential. So water potential is a measure of the energy available for water movement. The most energy would be when you don't have any solutes.
Those ones normally don't work.
Just in general.
Yeah.
So it measures the ability of water to move, and it always moves from an area of high water potential to an area of low water potential. So as we talked about with movement of water, solute concentration plays a role. So this water outside of this bag had 0 solute, so it's 100% water, which plays a role with water moving in, having a higher water concentration outside. Let me ask you this, if I took this bag and physically squeezed it and increased the pressure on this bag, have I changed the likelihood of this water to move out? Yeah, if I put pressure on it, I could squeeze and push that water out of those pores and increase the likelihood of that happening. So what we're going to do is look at water potential takes into account water moving not only based upon solutes, but taking into account pressure. What kind of cell have we talked about that pressure might play a role in water movement? Remember plant cells with the rigid cell wall, and when water, if it's in 100% pure water, water will keep on moving in, but will it keep on moving in forever? No, because what happens is that cell wall won't expand anymore, it's rigid, and so the cell will be filled with water, and because of the pressure buildup inside, no more water can come in, even though it's 100% water on the outside. And so therefore, pressure will play a role, even though you don't have equal concentrations of water, the pressure buildup will stop the water from going in. So we have an equation to figure out water potential. Water potential, we use this Greek symbol psi. Water potential equals, and there's two parts to it, the psi with a sub p, that's the pressure potential, and a psi with a sub s, and that's the solute potential. So we look at, if I have a beaker of pure water, all right, and so this is 100% distilled water. So inside this water, any solutes? No. And so therefore, the solute potential of pure water would be 0 because there's absolutely no solutes in it. It's open to the atmosphere. Is there atmospheric pressure? Yes, the atmosphere puts pressure, but it puts pressure on everything on the earth. And so what we do is we say that if it's just open to the atmosphere, everything is open to everything that is exposed to the atmosphere has the same atmospheric pressure next to each other. So if you have a cell and the solution surrounding the cell, they're exposed to the same atmospheric pressure. So when we say that we're not adding any additional pressure, we say that the pressure is 0, all right? So when we're not adding any additional pressure. So pure water has, as long as it's just open to the atmosphere, no pressure and no solutes. Let me give you an example of increasing or changing the pressure. So let's say I had another setup here where I had a beaker and I had a selectively permeable membrane that separated from the two sides of my beaker. And on the one side, I had solutes dissolved in my water, so the red is my solutes. And on the other side, I didn't have solutes, so it's 100% pure water. So as long as the openings, the pores in the selectively permeable membrane allow water to move, where's water going to move? To the left or to the right? It's going to go to the left, all right, from 100% pure water to something else that's not 100% pure water. Let me show you how pressure can change something. So this is both sides are open to the atmosphere. And so since both are open to the atmosphere, we don't count atmospheric pressure because it's going to have the same effect on either side. So therefore, it's not something that we would take into account. So when we're talking about pressure and the role of pressure in which way water is going to move, we're talking about additional pressure other than the atmospheric pressure. So what would that be? So pretend like I took on this side a plunger and pushed that down just on that side. Is that going to affect the movement of water on this side? Yeah, it's going to force it into this side. So it's going to move in a direction other than the concentration gradient, right? And so that's showing you that, yes, solute plays a role, but pressure can also play a role no matter what the solute is. And so you have to take into account both those things. When you don't have any pressure, open to the atmosphere, pressure is not an issue. It's just the solute you would be taking into account. All right? So pure water, let's write this down. So pure water at atmospheric pressure has a water potential of 0 because there's no pressure and no solutes. what we're gonna do is take a look now at each one of these parts of water potential and see how they affect water's ability to diffuse from one place to another. So we're gonna take a look at the solute potential first. So solute potential. The effect that solutes have on a solution's overall water potential. So when you add solute, so this picture here, if this is pure water on the outside, all right, and you put a sol in here, and so if I were to take this pure water with no solutes and add solutes to it, when I add solutes, am I increasing or decreasing the likelihood of that water going into the cell? Increasing it or decreasing it? What do you think? When you add solutes, what are you doing to the concentration of water? It's going down, right? And water goes from high to low, right? So if you add solutes, you're the more solutes you add, you're decreasing the likelihood of that water to diffuse. Does that make sense? All right. And so look at this equation. So a solute decreases the potential for that water to move in to the other solution. So we look at the mathematical equation. Water potential is pressure potential plus solute potential. So we just said solutes lower the potential for water to move to another place. So mathematically, what kind of number must the solute potential be to lower the water potential? A negative number, all right? And so when you add solutes, it's a negative number. Let's look at why that is. Water, pure water, has a water potential of 0. No solutes, no pressure. You add solutes to the water, it lowers the water potential. So if you start at pure water at a water potential of 0, add solutes and it lowers the water potential, it becomes more and more negative. Does that make sense? Okay. And so the addition of solutes lowers the water potential. So therefore, this solute potential mathematically in this equation is always negative. And I wrote here what I just said about water, pure water, because pure water has a water potential of 0, so any solutes will make the solution have a lower or more negative water potential. back to the equation here. So this is always a negative number, which then is going to decrease that water potential. All right, so it's always either the solute potential, if it's pure water, is going to be 0, or it's going to be some negative number. And the more negative, it means the more solutes are dissolved. Okay? So what I'm going to do now is show you how to calculate the solute potential. So I've been putting bullets here. So our fourth bullet, I have to switch things here because I decided to put it in here. So this is your fourth bullet. We're going to calculate solute potential. And this is the equation for this. You don't have to memorize this equation. It will be given to you like on a test or on the AP test. This is the equation. Solute potential is equals negative ICRT. Where, and I'm going to tell you what all those things mean. Okay, so I here is what we call the ionization constant. I'll explain why I have these underlined here. Ionization constant, and I put in parentheses that it's 1 for sucrose. What we're going to be doing in this class with this, we'll use 1. All right, we're going to use sucrose as examples. What an ionization constant means, when sucrose dissolves in water, sucrose is covalently bonded to one another, so it doesn't ionize or dissociate into ions when it's dissolved in water. Sodium chloride does. Sodium chloride is an ion. Sodium has a positive charge, chloride ion has a negative charge, and they bond together. When you put them into water, they dissociate to the sodium and chloride ions. And so for sodium chloride, the ionization constant is 2 because it dissociates into 2 ions. For this class, we're going to be using sucrose as an example. Anything I've ever seen on anything from the AP College Board has always used an ionization constant of 1. So we'll use 1 and know, we just need to know that that's 1 for the sugar sucrose. So that's a constant and something that we don't have to calculate. C stands for the molar concentration of the solution. Molarity is measured in moles per liter. R is the pressure constant, and this is always going to be the same. It's 0.0831 liter, lots of units here, liter, bars, and liter is just like a liter, it's a volume. It's not liter bars as that's a new measurement, it's liter and then bars. Liter, bars, over 1 mole, and the K stands for Kelvin. That's a temperature measurement. You guys remember from chemistry, Kelvin? Or physics? You're doing chemistry too, right now?
Yeah.
All right. So, bars are a unit of measurement of pressure. So bars are a standalone unit of measurement. And then T, what do you think T stands for? Temperature. And this is in Kelvin. And so Kelvin, to calculate Kelvin, you take the degrees Celsius and add 273. Okay, so these two, the I and the R, and here are, the R is a constant. I, for a lot of what we're going to be doing, is just a 1 for sucrose. So the thing that varies is whatever solution you're trying to figure out the solute potential, whatever its molarity is, and whatever the temperature is of the solution. So like in this class, if we were doing a lab with it, it would be at room temperature. So actually, the beginning of next week, we're going to do a little lab where you're gonna actually figure out the water potential of some potato cells is what you're gonna be doing, all right? What the potato will be at room temperature, so I have a temperature gauge up here and I'll see what degrees Celsius it is, and that's the temperature we'll use in our calculations. So let's apply this to a problem here. So what I'd like you to do is figure out what is the solute potential of a 0.15 molar solution of sucrose at atmospheric pressure at 25 degrees Celsius. So what I'd like you to do is use that equation you're going to use that equation, and what I'd like you to do is write out the math, so with the units, because what I'd like you to do is some dimensional analysis where you're going to cross off the units. I want you to see if you can figure out what's the units that this solute potential is measured in. So not only figure out the numeric value, but what units they would be measured in. Big M is the the shorter one. But I want to show you all the leader because that makes sense. You guys want the big M that stands for molarity. Another way to say that is moles per liter. All right, so 0.15 M molar concentration is 0.15 moles per liter. Okay, so looking at this, this is what we should, so you have the solute potential equals negative, and then it's sucrose, that's an ionization constant of 1. The molar concentration is 0.15, but I'm gonna write it in moles per liter because that is how the units will cancel out to get the right measurement for the solute potential. Then we have the R, which is 0.0831 liter bars. And when it says per mole, Kelvin, that's in the denominator. And then your temperature was at 25 degrees Celsius, so we add 273 to that, and you get, what, 298 Kelvin. Now watch this in terms of canceling out. So the liter can cancel out, moles cancels out, Kelvin cancels out, and you're left with bars, all right? So what happens is then your solute potential is negative, the negative 3.7 if you multiply this all out, bars, and that's the unit of measurement, okay? And so that is the solute potential of that particular solution. So all of that is used to figure out this part in this equation. All right, so let's look at the second part of the equation then, is the pressure potential. The pressure potential, luckily the College Board doesn't want you to be able to figure it out, and so we're just, you just need to know conceptually. So the pressure potential is the effect that pressure has on a solution's overall water potential. Sorry. How do you think pressure affects water potential, the potential for water to move from one place to the next? Pressure going to increase or decrease the likelihood of that water moving? Julia?
More pressure would increase the likelihood of water moving across the membrane.
That's right. So the more pressure, the more likelihood that that water is going to move across the membrane. So an increase in pressure potential results in a more positive value of our water potential. So this is going to become more positive and therefore increase that water potential. So increases the potential for water to move into the other solution. Does that make sense? Pressure?
So space less. So like if you have a solution or something like space.
Right. So, but usually you're comparing it from one solution to another. So if they're both in space, they both have no, like, you know what I mean?
Yeah.
So it's,
Yeah.
yeah. So knowing this, if we go back to that question about the one that we just figured out the solute potential for. Go back to this question here, and we just figured out the solute potential. If I were to ask you to tell me now for this solution, what's the water potential? Could you tell me? How do we figure out water potential? Pressure potential plus the solute potential. All this calculation just gave us this. So it gave us the solute potential. It's negative 3.7 bars. Do we have any information about the pressure potential for this solution?
The atmosphere, there's no atmosphere. Alright, sorry, we only have atmospheric pressure, there's no other pressure on it.
That's right. It's at atmospheric pressure, there's no additional pressure. So when that's the case, we say the pressure is 0. So therefore, in this case, when there's no pressure, the water potential is equal to the solute potential, and the way water moves is only based upon the solutes. Does that make sense? So you really have to pay attention to the stem of a question as far as if it ever says at atmospheric pressure or open to the atmosphere, that's telling you there's no additional pressure and that the pressure potential is 0. All right? All right. So on the things that you picked up today, I mean, this handout here is just some information about water potential. I want to give you something besides the notes because it's not in the book. So it goes through some examples and so on. So this is just reference for you. And then there is a sheet that says AP water potential sample questions. This is going to be due on Tuesday, okay? So you might want to write that down Tuesday. Just some practice problems. They start out easy and get progressively more difficult, a little bit more thought-provoking, and so on. So that's that. And then this last thing that you picked up here, just hold on to. We'll address that next week, okay? All right, this is where we'll stop.